Hello everyone, and thank you for joining me today. Today I will be presenting a recent paper titled Inverse Optimization with Prediction Market, a characterization of scoring rules for enacting system states. This paper is recently accepted by a famous conference. Let's begin. Let's start with a basic introduction for inverse optimization. In simple terms, inverse optimization is process of identifying unknown parameters or states in a system by looking at the outcomes that system has produced. Is a bit like working backward. Instead of starting with known parameters to predict outcomes, we start with observed outcomes to infer the parameters that might have caused them. This technique has a wide range of applications. For example, in system identification, we might use inverse optimization to estimate transmission times for seismic waves. When an earthquake occurs, the transmission time for seismic waves can tell us something about the unknown characteristics of the region they pass through. In outcome-aligned design, inverse optimization can help us achieve specific traffic patterns by adjusting tolls. If we know the desired traffic flow, we can work backward to figure out the tolls that would create that flow. And in inverse optimization, optimal transport, we look at observed transportation costs and patterns, trying to align them by figuring out the online transportation costs that would explain these patterns. So, inverse optimization is crucial for situations where identifying underlying parameters is crucial to decision making. This work lays the foundation for understanding how systems work from outside by looking at outcomes, and the primary goal is to work backward from unknown results to discover the factors driving them. While inverse optimization is a powerful tool, there also exists some challenge. For example, it is very challenging to apply it in practice. What the main challenge is ill-posed nature. This means that multiple states or parameters can produce the same observed outcomes. So if we only have the outcome to work with, it's hard to tell us which state is the true one, because different states might look identical in terms of results. This figure shows the relationship between an linear programming cost vector theta and the linear programming solution omega star. The LP cost vector theta must lie in the normal cone n times omega to the omega star. Conversely, any cost vector lying in the normal cone, that is the blue area, this area, results in the same linear programming solution, omega star. Another big challenge is subjective bias. In traditional approaches, a central decision maker, called the principal, decides what parameters to prioritize, often based on their own perspective. This principal may have specific goals or preferences, which can introduce a lot of bias into the outcome. For example, they might choose parameters that are close to a reference state that they prefer, which could lead to biased or unfair results. Finally, there exists the issue of inductive bias. Since inverse optimization is ill-posed, principals often impose additional constraints to make the problem solvable. They might, for instance, prefer solutions close to a certain reference point. This makes the solution mathematically well-posed, meaning it's easier to solve, but at the same time, it adds more subjective elements to the process. So, given these challenges, we need a new framework to inverse optimization that can reduce subjectivity and provide more objective results. The main goal is to create a system that doesn't rely on the principal's personal choices or preference. Instead, the proposed solution is to use prediction markets. In a prediction market, a group of agents, each with their own beliefs, submit their predictions or estimations about a certain outcome. Over time, these predictions aggregate to form a consensus that reflects the wisdom of the crowd. By using this collective intelligence, we avoid only relying on the principal's viewpoint and instead let the crowd determine the optimal state based on a democratical process. This helps us reduce bias and make the inference process fairer and more objective. To understand the proposed method, let's first look at what are prediction markets. Prediction markets are platforms where individuals, whom we will refer to as agents, submit predictions about a future event or outcome. These predictions are then combined or aggregated in a way that produces a single consensus-based estimation of the outcome. Prediction markets are valuable for several reasons. They let us get different opinions from diverse perspectives, providing a consensus that's based on a range of different beliefs and insights. This consensus is called market equilibrium, and it represents a balance of all the agents' input. The bigger advantage here is that it's democratical. Instead of depending on a single decision maker's perspective to determine the outcome, we get a crowd-based viewpoint that is likely to be more objective and representative. In the context of optimization, this consensus gives us a way to define the optimal state based on collective beliefs rather than individual bias, which is often fairer and more representative, and exactly what we are aiming for with inverse optimization. Here is how we use prediction markets to reformulate the inverse optimization problem. Our goal is to replace the principal's subjective choices with a crowd consensus that represents a more objective view of the optimal state. This process will work like this. First, we allow agents who are participating in a prediction market to submit their own beliefs about the state of the system. Each agent essentially gives us their own version of what the system's parameters or states should be. Then we aggregate these beliefs to reach a consensus that represents the crowd's collective view of the optimal state. This consensus is the new objective state, which is created through the crowd's input, rather than relying on a single principle's judgment, reducing the risk of individual bias and helps to improve the objectivity of the inferred solution. Now let's look at how the authors apply these ideas in the context of an inverse linear program. The objective in inverse linear program is to infer the state or cost vector of the system based on the observed outcome. Agents submit their beliefs about the states that could have produced this outcome, and these beliefs helps us identify which state might be the true one. One way to simplify this process is by using normal cones, which are mathematical structures that define feasible regions in the solution space. These regions helps us understand which states are possible and which are not, based on the observed outcome. By using normal cones to narrow down the solution space and crowd-sourced beliefs to identify the state, we can effectively estimate the most likely state that led to the outcome, that's shown like this figure. The authors formulated inverse linear programming as the report game with several tweaks to decision game. Let's take a closer look at an inverse linear programming game structure with this comparison figure. This figure shows the difference between the inverse linear programming game and the traditional decision game. The inverse linear programming game is used in the proposed approach. In the traditional decision game, on the left of the figure, the principal starts by choosing a state, and the agents then report their belief about the outcome based on the state. This process flows from the agent's reports to the principal's action, which produces an outcome, and then finally back to another report from the agent. In other words, the principal takes an active role in deciding the state, with the agent responding to this choice. On the right of this figure, it is the inverse linear programming game structure that is proposed in this paper. Here, the authors change the roles. The process starts with the agent reporting a conditional belief about a state based on the observed outcome. The principal, instead of choosing the state, plays an action that depends on the outcome space, taking the agent's beliefs into account. The process flows from the agent's report to the outcome the principal chooses, then to the inferred state, and back to a new report. The key difference is that the inverse linear programming game, the agent is the one driving the inference. The principal takes a backseat, following the consensus formed by agents. This setup aligns with the goal of creating an agent-driven, crowd-based approach that reduces subjective bias and gives more weight to collective beliefs. In the inverse linear programming game setup, it's crucial to have a mechanism that encourage agents to report their beliefs honestly. This is where proper scoring rules come into play. A scoring rule calculates a score for each agent's report based on how closely it matches the actual outcome. In the proposal framework, the authors use a strictly proper scoring rule. This type of scoring rule is designed to ensure that agents the score will maximize their score by reporting their true beliefs rather than guessing or manipulating their responses. There are a few common examples of strictly proper scoring rules, including the log score and the Brewer score. These score rules assign higher points for accuracy and encourage agents to be truthful, which is essential because we want the crowd's consensus to be as accurate and representative as possible. To make this process more efficient and limit the principal's influence, the authors implement a Zuckerberg model within this framework, which is a theoretical uh, game theoretical model. In this model, the agents act as leaders, and the principal takes on the role of a follower. Here is how it works. We can see how it works from these 3 points. The agents, as leaders, submit their beliefs, which guide the optimization process. Once these beliefs are aggregated, the principal accepts this consensus as the final solution. This model is powerful because it changes the focus from the principal's perspective to the agent's collective view. By following the crowd's equilibrium, the principal's subjective influence can be reduced, making the optimization process more crowd-driven and objective. This figure provides a dual perspective that captures the relationship between agents' beliefs and underlying uncertainty in the inverse linear programming game. This duality is a powerful concept that helps us interpret agents' beliefs within the optimization framework. Here, at present, we can analyze this figure in detail. We can break this figure down. On one side, we have what's called the MAP state, which is essentially the most likely state, according to the agent's reported beliefs. This MAP state gives us the optimal state from the agent's perspective. We can see that this is the MAP state we can see from this figure. On the other side, we have the regularized outcome, which reflects the system's uncertainty about the outcome. This regularized outcome represents the principal's perspective and aligns with the uncertainty. This is a regularized outcome. We can see from this part. We can say these two parts are inverse. The figure shows us a commutative diagram where agents' beliefs map to these optimization assumptions, helping us understanding how beliefs and outcomes are interconnected. This duality is valuable because it shows that agents' beliefs about state are not isolated. They are tightly linked to the system optimization uncertainty. By using this structure, we can collect all the agents' beliefs to the actual variability in the outcomes, which adds an extra layer of robustness to this approach. In fact, this paper has made several key contributions to the field of inverse optimization. First, it derives novel scoring rules that are specifically designed for inverse linear programming. These scoring rules are strictly proper, which means they ensure agents are motivated to be truthful in their reports. Next, the author structured the entire process as a stackboard game, where agents lead and the principal follows. This structure minimizes the principal's influence, so we get a solution that better reflects the collective view. Finally, they explore the dual perspective, the relationship between agents' beliefs and the inherent uncertainty in optimization. By understanding how beliefs and uncertainty are collected, we can better interpret the results of this approach and make inverse optimization more reliable. Then let's talk a bit about the computational aspects of this approach. Calculating proper scores, especially when dealing with strictly proper scoring rules, can be complex and requires significant computational power. Similarly, implementing the decision rules that have been used in this model isn't trivial. To manage this, the author used efficient strategies such as log concave exception, which help simplify the computation. However, as outcomes space get more complex, these computational demands will inevitably increase. A large challenge is scalability. As the outcome space grows larger, the computational load increases significantly. We have to keep these scalability concerns in mind, especially when considering how this approach might be applied to larger datasets in real-world application. Despite the computational challenges, this approach has great potential for practical applications across different fields. One example is traffic management. In this scenario, we could use inverse optimization to set tolls that carry specific traffic patterns, such as reducing congestion in certain areas. By relying on the crowd beliefs rather than a single decision maker's choices, we get a more democratic and potentially more effective solution. Another example is seismic analysis, where we might estimate seismic transmission times after an earthquake by inferring unknown parameters objectively. We could achieve more accurate prediction. This approach is also generalizable to any field that requires state estimation from observed data. By using cloud input, we can achieve a fairer, more accurate understanding of the optimal state in each of these cases. So we can say that the strategies proposed in this paper have a promising potential for the practical application. But there exist some challenges to implement this proposed framework. This method has its limitations. Scalability is a major concern. As I mentioned before, This computational causes the computational overhead will rise with larger datasets. This is something we will need to address for broader application. Another challenge is ensure there is enough participation in the market to reach a reliable market equilibrium. If too few agents participate, the consensus might not be representative, and the solution will be less reliable. Finally, the authors assume that agents report their beliefs truthfully, while strictly proper scoring rules encourage this. In practice, there may still be instances where agents don't act completely honestly. Managing these potential issues of strategic behavior and incentivization is something that is needed to explore in the future work. And there are also some minor concerns. For example, the robustness. In this paper, there's there's a neat analysis about the robustness to noise or incomplete data. Another minor concern is the potential manipulation. Strategic behavior by agents will be not fully addressed. Let's now talk about how this paper builds on existing research and offers something new to this field. Traditional approaches to inverse optimization are often heavily influenced by the principal's subjective choice. This approach, in contrast, uses prediction markets to produce an objective, consensus-driven result that is not tied to any one person's perspective. The authors have also created global scoring rules that are specifically designed for inverse linear programming, which is a technical contribution to this field. These scoring rules ensure that agents have incentives to report their beliefs accurately, which strengthens the reliability of the results. Finally, the Starkburg model that we use represents an innovation in how inverse optimization problems are structured, changing the control from the principal to the crowd. This change is significant because it democratizes the process and makes it more transparent and fair. So maybe in the future we can change this. We can use another game model to model the inverse optimization problem. For example, in this paper, it uses the Starkburg model to model the inverse optimization. In fact, we can compare different game models uh, and compare their performance on different tasks. In conclusion, this paper represents a new framework for achieving objective state inference through prediction markets. By moving away from a single principal perspective and instead using crowd consensus, the subjective bias is removed from the equation. This makes the entire process more democratical, fair, and ideally more accurate. This approach introduces new theoretical foundations for inverse optimization with specifically designed scoring rules, a Starkburg structure that empowers agents and a dual perspective on beliefs and uncertainty. Looking ahead, we see several directions for future work, including improving scalability, enhancing the robustness of this model, and addressing strategical behaviors in agent reporting. The framework has many potential applications and is believed to have the power to bring more fairness and accuracy to the invoice organization across many fields. In fact, there are many future directions. For example, we can adaptively using different game models to model the inverse optimization. On the other hand, we can also design different scoring rules, and according to each case, we can adaptively choose the most appropriate scoring rules. In this case, to ensure the honest report of each agent. Thank you all for your listening. That's all. That's all for today.